Hey class, welcome to our lecture on Chapter 2 from Natural Disasters. This week we'll be covering Chapter 2, which will be on the internal structure of Earth and on plate tectonics. So, when it comes to understanding the root cause for many of the natural hazards that we experience on our planet, plate tectonics is the first thing that you want to know about. Some of the hazards that are more related with plate tectonics are things such as earthquakes, volcanoes, tsunamis, landslides to a certain degree, soil subsidence to a certain degree as well. And those hazards themselves are again related to other ones as well. So in the concept of environmental unity, as we saw in the last chapter, these hazards are connected with one another. So this is a super key chapter to understand, so make sure that you are paying attention throughout the whole lecture. So whenever you're standing on Earth, either say on a mountain, or you're by the river, or on some vegetated soil, or wherever you may be, you'll be standing on the surface of the Earth, right? And most times, as we are going about our day, we don't often think about the underlying processes that are deeper within the Earth, deeper than the surface. We don't really think about the thousands of kilometers of rock and of molten material that really lie below our feet. But only about a few meters below our feet and, a little bit above the surface as well. So those are the only ones that we tend to think about. What is going on immediately right below me or immediately right above me? Perhaps when you're thinking about the atmosphere, you think a bit further, but even so, we don't think about what's going on deep within. So the first part of this chapter focuses on the layers that make up the Earth itself, the subdivisions of the Earth, let's say, in their chemical and in their physical characteristics specifically, which play a very large role in understanding plate tectonics, and hence some of the processes that occur due to the plate's actions. So the learning objectives of this chapter will be the following. First, we'll go through understanding the basic internal structure and processes of Earth. Second, we'll cover the evidence for the theory of plate tectonics. So here we'll cover the ideas that came before the theory of plate tectonics. We'll cover the transition that happened in geologic sciences, more specifically, but also in other sciences related, from not having any underlying continental movement ideas and transition into the continental drift hypothesis of the earlier 20th century, and later to the eventually well-recognized theory of plate tectonics. The third objective that we have for this chapter is for you to understand the mechanics of plate tectonics themselves. And the last objective is to understand the relationship of plate tectonics to natural hazards, which is the main objective of this class. So as I said in the previous slide, several of the types of natural hazards are linked to plate tectonic movements, and so understanding the dynamics of plate tectonics will help us understand the natural processes that are linked to those hazards. Again, those hazards being things like volcanoes, earthquakes, tsunamis, or landslides. So as I said in the first slide, most people don't tend to think about what there may be beyond a few meters below their feet. Some people think that the Earth is a big orb of rock. Some other people might think that it's mostly a massive magma pool that sits just a few kilometers below the surface. But in truth, the Earth is a bit of both. The internal structure of the Earth is layered and it is dynamic, meaning that there is material exchange between the layers that make up its structure. So the layers that make up the Earth are made of different materials, which in turn make them be more rigid or more molten. The classification that we use to explain and subdivide these layers are then based on the chemical characteristics of the Earth, right? But also on the physical characteristics that make the two different classification system schemes. So chemical and physical. The chemical classification structure is based on the material composition that makes up each of the Earth's layers. What are the main chemical elements that make up the layers, basically, is what it gets to. Along with the composition, the density of the material in each layer is another deciding factor for the subdivision of this classification structure. So both composition and density. So for example, one of the layers of the Earth has more iron than the others, and it is more dense. Iron is an element that is quite dense itself, as it is heavier than other common elements, but it also occupies about the same space or nearly the same volume. So the composition of that layer is also the main reason for the density difference between that layer and other layers. So composition and density are pretty well correlated to a certain degree. The physical classification structure is based on mostly on how fluid the material is going to be. So the specific subdivision and the depth of each layer were basically pinpointed in the 20th century when we were able to use seismic wave reflectance to see how fast or how slow the seismic waves moved through each layer, which in turn also allowed for us to infer how fluid or how rigid each layer was. And we'll look at this in more detail as we go through the chapter and on chapter 3 when we cover earthquakes and seismic waves with more detail, but for now that should be plenty. So this diagram that you have on the slide is an image from your book, so if it's hard to see, go ahead and refer to your book for further detail. You will see this exact same basic image in the next few slides as well. Maybe a few things will be cut off, but basically same image. So again, if you need to refer to it, I would go to your book. So as you can see, the diagram has a depiction of the inside of the Earth, and on either side of that depiction you can see the two different classification schemes, right? So you have physical properties right here, chemical composition right here. You can see the name of each layer, so it's hard to see obviously with this zoom or with this magnification scale, but you can see that this, for example, is the inner core, this is the outer core. This on the chemical classification just is made up of core per se, and we'll go through why that is. You can also see the depth of each layer on either subdivision, so it tells you how far from the surface each layer is. You can see the density of each layer for the case of the chemical subdivision. So here on the chemical side, you see that the core is 10.7 grams per centimeter cubed. We'll go through all that. And you can also see the nature of the material for the case of the physical subdivision. So at times, they will actually tell you what it is made out of, sort of, or how thick it might be based on that. So as you can see, the chemical subdivision is made up from core, mantle, and crust, going from the center of the Earth out into the surface. And then the physical subdivision is made up from the inner core, the outer core, the mesosphere, the asthenosphere, and then lastly the lithosphere. It's hard to see from this image, but as you see on this box, they expand it, and you see the mesosphere here again below, right? The asthenosphere following it, and then lastly the lithosphere, which makes up the top part. And you can see it right here. Here's a label for it. So in the coming slides, we'll go through each of these layers in either of the subdivisions, all right? All right, so now we're going to go ahead and cover the subdivisions of the Earth based on their composition and on their density. So based on the chemical classification, basically. But we'll also cover the layers per se as labeled in the physical properties. So even though we're covering composition and density, you see that we do split it into inner core and outer core. Okay, so it's kind of a mix of both, but we'll touch each of the layers that we need to. So the first layer that we'll talk about is the inner core. So the inner core is the centermost layer of our planet. It is solid, and mainly it is solid because of the gravity and rotational forces, which have caused the very dense particles out of which it's made to settle deeper and deeper into the planet itself. The inner core is about 750 miles thick, so quite thick, about the size of the moon. So you can think of the moon as being that big, but obviously not within the Earth, much, much further. So it's very hot as well. nearly about the temperature of the surface of the sun. So incredibly hot. And as we'll see later, part of the heat that we have on Earth comes from this low cooling, if you would, from the core outwards, that it expresses outwards, or the heat moves outwards into the surface. So the two main elements that make up the core are the inner core are iron, which is the largest element in percentage by far, and nickel, which is the second most common. It does not contain, it does contain some oxygen and sulfur as well, but these are trace amounts in comparison to the iron and the nickel. And then other elements can also make their appearance within the core, but their abundance in the inner core is so minimal that I don't even mention them within the PowerPoint slide for you. The density of the inner core is 10.7 to 13 grams per centimeter cubed. To some of you, this may not seem like a lot, or perhaps it may just, you may just hear the number and not think much about it, but as a comparison, liquid water at the surface is 1 gram per centimeter cubed. So again, 1 gram per centimeter cubed is water, so you can think of a bucket of water and how heavy that might be, right? Well, the inner core is again 10.7 to 13 grams per centimeter cubed. That means that it's 10 to 13 times heavier for the same bucket that you would be carrying. So you can simply imagine how much denser the core really is. Another comparison is, for example, gold. Gold is 19.3 grams per centimeter cubed, so much, much denser than water and quite a bit denser than the inner core. But it gives you kind of an idea of how heavy each chunk of the equal volume of these materials has to be. The outer core, which lies just right above the inner core, right? So inner core is right here, outer core is right here. Is nearly twice as thick as the inner core. It has the same composition, however, as the inner core, and it's nearly the same density. So it doesn't range all the way to 13 grams per centimeter cubed. So we keep the density at 10.7 for the whole core when we average it out. But it's about that much. So it is on the lower limit of the density. Since it has the same density, that is why in the chemical subdivision, these two layers are simply one as the core, right? Because they contain iron and nickel, both of them, and they have about the same density. The outer core, however, is liquid, unlike the inner core, right? Which was solid, which is why we really do subdivide the two in the physical subdivision, because one, again, is solid in the middle, the other one is liquid. Again, the outer core being more fluid than the inner core, the reason for this is because the gravitational and the rotational forces don't make as big an impact on the outer core as they do on the inner core. So the material still remains hot enough for it to be more molten, and yet not as compressed enough to become solid. So that is why it is fluid rather than solid like the inner core.